Okay, so at this point, we now need to start learning how to solve differential equations. And in order to do that, integration plays a pretty important role at first, especially with the first order differential equations that we're going to start solving. So you now need to know how to integrate. And at this point, by the time you're in differential equations, that should be no big deal. But you really should know your basic integration. Here's a list of some real basic integrals that everyone should know. Go through them real quick. Obviously, power rule, right? Raise x to the higher power and then divide by. Everything has a plus c on it, so I'm just going to skip that from here. 1 over x, that's your log x. E to the x is e to the x. Sine x is going to be your minus cosine x. Cosine x is going to be sine x. Secant squared x is going to give you your tan x. Secant times tan, that's going to give you secant x. And these are just because you know your basic derivatives. You also know your integrals. Cosecant squared is going to give you minus cotan. Cosecant x, cotan x. This one's going to give us your minus cosecant x. Secant x, this is where we start to need our logarithms. So this will be natural log of secant x plus tan x. Integral of tangent is going to give you your other natural log. That's going to be minus natural log of cosine x. Sometimes you also see this as the log of the secant x. Depends on how you want to write it. So if you put this as an exponent inside, and then cosine to the -1 is the same thing as reciprocal, and therefore it's secant. Here we get some of our inverse trig ones. So if we look at the first one, your a squared minus x squared, that's your arc sine. So this one would be arc sine of x over a. This one would be your arc 1 over a arc tan x over a, and this one's going to be your arc secant, so 1 over a arc secant of absolute value of x over a. Again, every one of these has a plus c on it. I'm just not going to write that. Cosecant x by itself is going to give you your natural log, negative natural log of the cosecant x plus cotangent x. Cotangent x is going to give you the log of the sine. The integral of the logarithm, while this is not one of, say, like your basic integrals, it's a fairly complicated integral. It comes through integration by parts. And so what you need to do is, you would learn this logarithm by using integration by parts, but I think it's definitely something that's worth memorizing because log x is one of your basic functions, your basic transcendental function. And you would get x log x minus x. Integral of constant is going to be that constant times x. U dv is your integration by parts, which is u times v minus the integral of v du. And the integral of dx is just going to give you x. Okay? So these are your basic integrals. Everyone should know these at this point. You really should have them memorized. I really shouldn't even have to go through this in a differential equation class, but it takes a couple minutes. I just spent 4 minutes going through all that. It's worth it for you to make sure you understand this is the most basic things you need. If you can't do this, we can't move forward. All right, so the first type of differential equation we're going to go into, and this is for first order differential equations. And this whole first unit is going to be all about first order differential equations, where the highest derivative in the differential equation is a first derivative. We're going to go through this separable variables type of differential equation. It's the simplest one to do. It really just revolves around doing basic single variable integration. So let's look at a differential equation that's a first order in this form. So we've already seen that there's a bunch of different ways that you can denote a differential equation. One common way is to put the derivative, the highest derivative on one side and everything else on the other side. In this case, since it's first order, you have the first derivative on the left-hand side, and then the only thing left would be x's and y's. So you could say there's a function of x and y on the right-hand side. Now let's say that that function of x and y on the right-hand side is really only a function of x. There are no y's. Okay? So we have the dy dx equals g of x. Well, if I move this dx to the other side of the equation, and then I integrate both sides of that equation. So I integrate the dy and I integrate gx dx. Well, looking at them individually, the integral of dy is the derivative of y, right? So the integral of the derivative of y would just give me y. And then the integral of g of x dx, well, that's just a single variable basic integral. And then whatever the antiderivative of g of x is, say capital G of x, would be the answer for that side. And ultimately, here you go. Well, what is that? That is the solution to this differential equation. This is the most basic differential equation you could possibly come across. This is basically the definition you had for indefinite integration back in Calc 1, is essentially looking at, oh, I have the derivative of something, and it's this function, okay? What is that original function? And that's the antiderivative. So this is very basic. We're not going to be doing this a whole lot, but this is the basis for where we're going to go with this whole thing. So anyway, this is a fairly basic differential equation. It's simply just antidifferentiation. So here's one of those types. Here's another one of those types. They would be very easy to solve. And you're trying to figure out what function satisfies this differential equation. So in this case, if you did say this one, it would be very easy. You would do the y equals the integral of 1 plus x e to the 2x dx. And as long as you can do this integral, you got your answer. Well, you can very easily. Integral of 1 would give you x. This we need integration by parts to do. And if you did that, it would be pretty simple. You would have your u to be x. Your dv would be e to the 2x dx, giving you just du to be dx and v to be 1/2 e to the 2x. And then you go from there. So we get y equals x, that's from here. Then you have u times v minus v du, so you'd have plus x over 2 e to the 2x minus this integral, and then once you get an integral, you get minus 1/4 e to the 2x, throw a plus c on there, and there is your solution to that differential equation. But all you really did was real basic Calc 1, or in this case, since it's integration by parts, Calc 2 integration. This one, just as easy, as long as you know what the integral of secant is, and we do because we just went over that. That's the natural log of secant x plus tan x. You have the answer to that one. So this is too simple. We're not going to be doing this. This is what you were doing in Calc 1 and 2. What we're going to do is we're going to look at a differential equation like this, okay, where the right-hand side is not just a function of x, but it has also y's in it, but not just randomly y's. The right-hand side of this is a function of x divided by a function of y specifically, okay? Not a function of x times a function of y, although we can do that too because we just do reciprocal. But nonetheless, this can be written as a function of x divided by a function of y. And if we have a differential equation in this form, dy dx equals a function of x divided by a function of y, we call that a separable equation, okay? Or we say that the equation has separable variables. And we're going to take a very similar tactic to what we did here. So here are two examples. This one is separable because we can write it in that form that I just described. The trick is with this exponential function to write this as e to the 3x times e to the 4y. Adding in the exponent, you multiply in the bases, basic algebra. And then the trick is if we take this function that has a y in it and this function has a y in it, since they're exponential, functions with exponents, we just change the sign of the exponents, we could bring them to the denominator. So we would get dy dx equals x e to the 3x over y to the negative 2 e to the negative 4y. And there is your separable differential equation in the form that you want. This one is non-separable, and the problem here is really the addition. There's no way to write this as a quotient function of x over function of y, and the addition really messes that up. The fact that these are all multiplied together is why it's more workable to put into this form. So then we would be able to solve this using separable variables. Now, how do we do that? Well, the trick is exactly the sort of in the title is we would separate the variables. So when this function of y wasn't there, what did we do? We brought the dx over with the function of x. Well, what we're going to do here is we're going to do that by multiplying that dx to the other side, but I'm also going to multiply this function of y over to this side. So I'm bringing my y's over with my dy and my x's over with my dx, and I'm getting this equation. And if you notice, the variables are separated. Y is on one side, x is on the other. Then we're going to integrate both sides of the equation. The integral of h of y dy is just the antiderivative of that h function, and the integral of g of x dx is just the antiderivative of that g function, and there is my solution. Now, technically, this integral should have a plus c on it, and this integral should have a plus c on it, but the c here is not the same as the c here. Necessarily, they're both constants, but this would be a different constant than, say, this one. So if I call them C1 and C2, I could do that. But ultimately, if you notice, if I had h of y plus C1 plus g equals g of y plus C2, I could just move this constant to the other side of the equation by subtracting it. Now it's no longer there. But if you notice what this is, if I have one constant minus another constant, this is still just one giant constant here. So rather than call it separate constants, I just combine them together and call it c. So I really don't need a c on both sides. I can lump them all together as one big c on either side. It doesn't matter which side. And so separable variables is as simple as integrating both sides of the equation after you separate the variables. But the trick is being able to separate the variables, have only y's, and integrate that with respect to y, have only x's, integrate that with respect to x. You also don't have to put them on either side of the equation. I could also write it as integral of h of y dy minus the integral of g of x dx equals 0. I could have everything on one side of the equation, but I still have it grouped. Here's all my y's, here's all my x's. And as long as you can integrate this and this, you have your answer. Now, we've seen that differential equations can be written in all kinds of forms. The most common way a first-order differential equation is written is typically that the dy dx is split apart. And so we have some function dy plus or minus some other function dx equals 0. This is a very common way of writing a first-order differential equation. So as far as separating the variables goes, the dx and dy are already pulled apart. Now you just have to put x's with this dx part and y's with this dy. And if you can, then good. You don't have to go to this form, dy dx equals function of x over function of y first. You don't have to get to that point first. You really just need to separate the variables. So if you want to go here first and then separate the variables this way, fine. It doesn't matter. At this point, our algebra skills should be so in-tuned that we should be able to just work with this. So what I'm going to do here is I'm going to divide by 1 plus x, and if I divide that across the whole thing, that's going to move the 1 plus x over. It's going to cancel here, and this is 0 still because 0 over 1 plus x is still 0. And I'm going to do the same thing with the y. If I divide by y, here, here, and here, these y's cancel. Now the y is over here, and this is 0 over y still, so just still 0. So ultimately what I end up with is dy over y minus dx over 1 plus x equals 0. Now I have my variables separated. I'll integrate every piece. Okay. I'm really integrating both sides of the equation, but since there's a minus here, I can integrate these pieces separately. And ultimately I'm going to get the natural log of y minus the natural log of 1 plus x equals c. Integral of 0 would be c. I should say there's a constant of integration for this integral. There's a constant of integration for this integral. But if I pull those two constants over to the right side of the equation and lump them with this other constant, I still would just have one giant constant here. So I just ignore all that and just say, okay, now I have c here. Now, this is not typically the way you're going to see the answer written. It would be nice if we could write the answer in explicit form, y equals, in this case, say some function of x. Okay, if we could write the answer that way. We're not always going to get to do that, and sometimes, it's fine if we can't do it. But if we can easily get to the explicit form, we tend to try and do that, and we can do that here. And this is something you're going to have to get used to, because you're going to solve these differential equations, say for homework. You're going to look at the answer in the book, and it's not going to look like the answer you got. That's because they manipulated it a little bit, and you're going to have to get used to how this is done. So first thing we're going to do is we're going to bring these two logs together here. And so we're going to have the log of y divided by 1 plus x. The reason why it's divided is the subtraction turns into division equals c. Then I'm going to exponentiate both sides. I'm going to raise both sides of this equation to the exponent of a base e. Okay? What that does is it uses the inverse property to cancel the e in the natural log. And the other side, we get e to the c. Now think about it. C is a constant. E to a constant. E is also a constant. So e to a constant, this whole thing is still just a constant. So I'm still going to represent this side as just c. Now this c here is different than this c here, if you really think about it. So if you wanted to, we could go back and call this C1, and now we can call this just C. Ultimately, it doesn't matter in the end, but you should recognize that these two C's are now different. This C right here is e to the C, and this C right here is just C itself. But it makes it look a lot nicer, recognizing that it is still just a constant, so we'll call it C. So where are we here? What we end up with is y over 1 plus x equals C. If I then multiply the 1 plus x to the other side, I have c times 1 plus x. And now I have that explicit form fairly easily. It didn't take long to get there. So if we can do that, that's preferable. Again, not completely necessary. You can have implicit solutions to a differential equation. Sometimes that's all we're going to do, right? We're only going to have implicit solutions. But if we can get to that explicit form, we tend to try and do that. So here's another example. In this case, this one already has that proper form of a separable equation. We have a function of x over a function of y, and we have this initial value part. But this is really something to be ignored for right now, because this will not play a role until we actually solve the differential equation. So we separate the variables. So let's go y dy equals negative x dx. Put the negative somewhere, whether it's on the left side or right side. Integrate both sides. And so ultimately what we're going to get is y squared over 2 equals negative x squared over 2 plus c. I'm going to play with this a little bit. I want to make it look a little bit nicer. This is fine, but we could definitely clear this out a little bit better. What I can do is I can multiply this whole equation by 2. Now, why do I do that? Because it allows me to not have to look at these fractions. And not looking at the fractions is a little bit nicer. This right here would be 2c. Well, 2 times a constant, you've already kind of caught on at this point, is still just a constant, so I'm just going to call that c. And so that c is definitely different than the c I had a second ago, but still it's just a constant. And so we have y squared equals negative x squared plus c. Finally, what I'm going to do is I'm going to bring this x squared over. I'm not going to put this in explicit form, which kind of contradicts exactly what I was just saying, in that if you can, you should do it. And it would be pretty easy to put in explicit form. Y, we'd just take the square root. We take the square root of both sides. We would have to make sure we had the positive or negative square root. Basic algebra would tell us to do that. But I'm not going to do that. What I'm going to do instead is I'm going to bring the x squared over to this side. I'm going to get x squared plus y squared equals c. And the reason I'm going to do that is this is graphically the representation of the solution for this differential equation. And you should look at this equation and say right away, geometrically, you know what that is on an xy plane. It's circle. Depending on c would be the different radii, or let's say the square root of c would be the different radii of that circle. But geometrically, we're saying that all these circles are solutions to this differential equation. It just depends on what radius we want, and that would be dependent on what c is. So now what we're going to do is we're going to then solve the initial value problem. So this is the solution to the differential equation. Now we want to solve the initial value problem, y of 4 equals 3. So basically what we're saying is there's this point, x is 4 and y is 3. And so we have this point, say 4, 3 here. We want to figure out, of this family of solutions to the differential equation, which is all these circles, which member of that family goes through this point? So which specific circle would have a radius that would cause the circle to go through that point? And that's the solution to the initial value problem. Well, the easiest way to do that is to plug this x value and this y value into the solution, in which case we would get 16 plus 9 equals c, which would be 25 equals c. And so the solution to the IVP would be x squared plus y squared equals 25. Really easy. So this is the solution to the differential equation, and this is the solution to the associated initial value problem. All right, here's another one. This one's more in that form that we saw with the first one, where the dy dx is split apart. Pretty easy to separate, though. This e to the negative y would just be divided over to here. So we would get x sine x dx minus, if e to the negative y is divided, I could also bring it up as an e to the positive y times y dy equals 0. And then integrate both of these pieces, as well as the other side. And we're going to need by parts here. So let's say u equals x, dv equals sine x dx. And we're going to need by parts here. So let's call this one u is y, and dv is e to the y dy. And so du would be dx, and v would be the integral sign, which is negative cosine x. Okay, and once we go through that, you do your u times v minus the integral of v du, and we can go from there. So what would we get? We would get negative x cosine x. Oh, geez, what's going on here? Negative x cosine x minus the integral of v du would be minus the integral of negative cosine, so basically just the integral of cosine, so that would be sine, so plus sine x. Okay? And this one over here, du would be dy, and v would be e to the y. So again, you have u times v. Okay? Don't forget there's a minus out here. So we could either do minus and then put parentheses for the whole thing, or I could associate this negative in with one of these two pieces here, say with the y, and basically it'll distribute its way through. Doesn't matter. I left it out from the start, so I'll just continue to leave it out. So let's say y e to the y minus the integral of v du, which would be this integral, which is basically just the integral of e to the y again. So we get e to the y. And the other side is the integral of 0, so that's where our c comes in. So clean this up a little bit. There's really not a lot we can do. I would probably distribute this now, in which case I would get negative x cosine x plus sine x minus y e to the y plus e to the y equals c. As far as writing this in explicit form, there's no way that's going to happen. We're never going to get this into a y equals a function of x notation, so there's no sense in doing this. This is just going to have to stay an implicit solution. Totally fine. Sometimes you just got to deal with that. There's no initial value problem in this one either, so we're done. There's the solution to our differential equation. Here's another one that we're going to look to try and separate. And if we can't separate it, right now, that's the only method we have for solving these. So if it's not separable, we really can't solve them right now, these first order ones. But This one will be separable too. I have this function of x here that I'm going to divide over to this side. I have this function of y here that I'm going to divide over to this side. So I'm going to end up with x e to the 3x dx plus y squared plus 2 divided by y to the 4th dy equals 0. Again, if I'm dividing e to the negative 3x over here, and it's in the denominator, I'm going to bring it up by making it e to the positive 3x, and that way this is easier to integrate. This one here, in order to integrate this piece, I'm going to separate this into two separate fractions, y squared over y to the 4th and 2 over y to the 4th. So when it comes to integrating both sides, I'm going to have the integral of x e to the 3x dx, which is going to need by parts similar to what we just did with the y's. And this one's going to end up being the integral of y to the negative 2 plus 2y to the negative 4, and that's as a result of me separating the variables in this fraction, y squared over y to the 4th, 2 over y to the 4th. Okay, so now we're all set to go for integration. By parts here, u equals x, dv equals e to the 3x dx, du is dx, v is 1/3 e to the 3x. So we're going to end up with x over 3 e to the 3x minus 1/9 e to the 3x, and that's because the second integral would be the integral of this. So the integral of 1/3 e to the 3x dx, which would be 1/9, plus, then we're going to integrate each one of these. So this would be what? So it would be negative y to the negative 1, and this one would be negative, 2/3 y to the negative 3 equals, say, c. Okay. Other than that, I mean, there's not really much to do here. We probably shouldn't leave these as negative exponents, so maybe we write it as x e to the 3x over 3 minus e to the 3x over 9 minus 1 over y minus 2 over 3y cubed equals c. You want, you could take this whole left side and put it as a single fraction. Not necessarily. You're not going to get it into explicit form, so there's your answer. All right, so we've seen that unless it's convenient, we can leave our answer in implicit form. It's totally fine. But if it's easy to go to explicit form, do it. I mean, that's usually preferable. And one reason why it's preferable is it's easier to check your answer if it's in explicit form. Now, we haven't been checking our answers, and you don't have to check your answers. But remember, the solution is the function that satisfies the given differential equation. So what function y, which is a function of x, right, could I plug in here that would satisfy this differential equation? So I plug it in here. I also plug the derivative of it here and makes this side equal this side. So having it in explicit form makes that easier to do, but, that's the only reason why explicit form, well, one of the only reasons why explicit form would be nice, but not necessary, right? Implicit form is totally fine. One thing to watch out for is when separating the variables. We haven't really talked about this a whole lot, but make sure the things you're dividing by when you're switching sides of the equation, so you divide to one side, divide to the other side, that they're not 0. Or at least you should recognize that when you divide by it, you're assuming that that function is no longer ever equal to 0. That comes up in this question right here. Okay? There's two versions of this question. One is not a problem, the other is. And the only reason I like to do this one is to show you that as long as you recognize this, okay, that once you start dividing a function from one side to the other, you're now assuming that the divisor is not 0. And if it is 0, you're throwing that possible solution away by dividing. Now, sometimes we don't have a choice, right? The only way to solve the differential equation may be to divide that function from one side to the other, which in thinking about it, I'd rather get the solution to the differential equation and throw out possible values of that function along the way than not get a solution at all. And so there's two versions of this question. One is, where we see here, where we're solving this differential equation, given this initial value. There's another one we could do too, the initial value being 0, -2. Now, thinking about this, these are points, right? This is a point 0, 2, and this is a point 0, -2. And I'm just kind of moving ahead and showing you kind of the final result, and then we're going to go back and see where some problems are. So this is a point on this equation, y equals 2. Y equals 2 is a horizontal line. It's a horizontal line that every point on this horizontal line has a y value of 2, so 0, 2 specifically, which is right here, is definitely on that line. Y equals 2 is also a solution to this differential equation, in that if you look at it, y equals 2, the derivative of that is going to give me 0. So if I plug the derivative of that in here, and I plug the y itself in here, does it satisfy this equation? Yes, it makes this side 0, and here I'd have 4 minus 4, so it makes that side 0, so yes, it satisfies that equation. So this is a solution to the differential equation. It's a solution to the differential equation that goes through this point, so it should also satisfy this initial value problem. Let's look at this one, y equals -2. Y equals -2 is a point on y equals -2. That's a horizontal line. The horizontal line that goes through -2 down here, you know, and all these other y values, all these other points have a y value of -2. So this point is definitely on this equation. And then if you notice, this equation also solves this differential equation, in that the derivative would still be 0, and I plug -2 in here for y, it would make 0 equals 0. So this should be the solution to the differential equation that satisfies this condition. But there's a problem with this. One of these will still come out of the solving process, and the other one will not. And it's because of this. This starts to throw some of this stuff off, and we lose solutions that should be there, but aren't going to show up because of the method of solving. Now, we only have one method of solving, so we don't really have a choice. You just have to recognize that this is a possibility that you're going to lose certain solutions. Okay, so let's go in to solve this differential equation first. Then what we're going to do is we're going to solve this initial value problem and this initial value problem and see where the issue comes in. Okay, so we have the differential equation dy dx equals y squared minus 4. Let's solve that first, and then we'll worry about the initial value part. So I can separate this. I can write this as dy over y squared minus 4 equals dx. I could integrate both sides. The right-hand side, very easy. The left-hand side, not so easy. The integral of dy over y squared minus 4, you start to think of how could I get that done? Well, there's two primary ways I would think about doing this. One is we could try and use trig substitution. I mean, we don't have the square root here, but those aren't really necessary. And the other is partial fraction decomposition. So both fairly, lengthy methods of solving, but there's really no other way. We don't have any basic u substitution I can do. Like if I had an extra y here, then it's real simple, right? I could just do, a u du and get it done, but that's not the case, right? So that y is not there. So I'm going to do partial fraction decomposition. I think that's probably one of the simpler ways to do it. So I'm going to look at just a fraction 1 over y squared minus 4, and I'm going to decompose that. So that's the same thing as 1 over y plus 2, y minus 2. So if I'm going to decompose it, I have two denominators, y plus 2 and y minus 2. This numerator would be, say, a. This one would be b. And I have to figure out what those constants are. Now, why am I doing this? I'm doing this because if this equals this, and I'm trying to integrate this, then ultimately I'm trying to integrate this. Now, if this is just a constant and this is a constant, the integral of some constant over y plus 2, that's an easy integral to do. It's a logarithm. And constant over y minus 2, same thing. So this is going to help me integrate as long as I know what a and b are. Well, the way you do your decomposition is you first clear the fractions out of this piece. So we get 1 equals a times y minus 2 plus b times y plus 2. We're going to say y equals 2, y equals -2. in which case when y equals 2, this becomes 0, so we get 1 equals b times 4, so b equals 1/4. When y equals -2, this becomes 0, so we get 1 equals a times -4, so a equals -1/4. So in the end, what we're really doing on the left-hand side is we're going to do the integral of -1/4 over y plus 2 plus 1/4 over y minus 2 equals the integral of dx. I'm just going to write as x plus c. So what we end up with here is -1/4 times the log of y plus 2 plus 1/4 times the log of y minus 2 equals x plus c, and I'm trying to cram that in there. Then what I'm going to do here is, I'm going to move down a little bit so I have more room. I'm going to try and simplify this a little bit. So a lot of what I'm going to do next is just rewriting this over and over again, and that's only because I'm going to go to the initial value problem next, and I want to make that initial value problem as easy to solve as possible. So I'm going to clear out these 1/4. I'm going to multiply everything through by 4. So I have the log of y plus 2, and that's got a minus in front of it still, plus the log of y minus 2 equals 4x plus 4c, which I'm just still going to call c. So I have to multiply the 4 over to the other side. Then what I'm going to do is I'm going to put these two logs together. This one being subtracted should go in the denominator. So I have y minus 2 over y plus 2 equals 4x plus c. Then I'm going to exponentiate both sides to get rid of the log. So y minus 2 over y plus 2 equals e to the 4x plus c. Now, this is all in the exponent, but I could write this as e to the 4x times e to the c, but e to the c is a constant, so I could just write this as c e to the 4x, and this is still on the other side. Okay. I'm going to keep going with this one. Again, I'm going to keep going with this one for one reason only, and that's so that the initial value problems, again, in the end, would be easier to solve. I can get this to explicit form, and that's what I'm going to keep doing. So we have y minus 2 over y plus 2 equals, let's see, e to the 4x, right? I'm going to multiply this to the other side, so y minus 2 equals ce to the 4x times y plus 2. I'm going to distribute this in, so y minus 2 equals ce to the 4x y plus 2ce to the 4x. Now right here, I'm not going to say 2c is just c, because that, now I have a c over here as well, and I don't want to now start using two different c's. So I'm going to stop doing that here, because I want to just keep this c as c. I don't want to have like this one be c1 and then turn this into, say, c2. So I'm just going to keep this as is. Then what I'm going to do is I'm going to bring this over to this side of the equation and this over to this side of the equation by subtracting and adding. So we get what, y minus c e to the 4x y equals 2c e to the 4x plus 2. Okay, then I'm going to factor a y out of here. 1 minus c e to the 4x. I'm going to factor 2 out of here. So this will be c e to the 4x plus 1. I'll divide this, and finally, y equals 2 times 1 plus c e to the 4x over 1 minus c e to the 4x. That was a lot, but it was just algebra, and it was really just to get to explicit form. Okay? All right. Anyway, there's your solution to the differential equation. So now we have this initial value problem. First was that y of 0 equals 2. Now, if y of 0 equals 2, that's your x, that's your y. Plug them in, you're going to get 2 equals, get rid of that. We're going to get 2 equals 2 times 1 plus c e to the 0, right? E to the 0 is going to be 1, so 1 plus c over 1 minus c. So I can divide by the 2 here, so I get 1 equals 1 plus c over 1 minus c. Move this to the other side. I can get 1 minus c equals 1 plus c. Subtract the 1 this way. Okay. Add the c this way. So I'm going to get 0 equals 2c. So c equals 0. All right. Well, if c equals 0, then that tells me that this should be 0 and this should be 0. So what do I get out of this? I get y equals 2 times 1 plus 0 over 1 minus 0. So y equals 2. Great. That's what I was expecting to get. Remember, this was a point on this equation, and this equation was supposed to be a solution to the original differential equation that satisfied this condition. So great, everything worked out perfectly. However, let's look at the other condition that I threw in there as well. The other initial value problem of y of 0 equals negative 2. So we had this y equals 2 times 1 plus c e to the 4x over 1 minus c e to the 4x. We now have this initial value of y of 0 equals negative 2, which we hope would pop out this y equals negative 2 solution. Problem is it doesn't. So we plug in 0 for x, negative 2 for y, so we get negative 2 equals 2 times 1 plus c e to the 0, which would be 1. So c times 1 over 1 minus c times 1. A lot of same stuff, divide by the 2, so we get negative 1 equals 1 plus c over 1 minus c. Move this to the other side, so times negative 1. So what does that end up giving us? It gives us a c minus 1 instead of 1 minus c, because by multiplying by negative, you just flip it. And then what happens is this. So if we try and solve for c here, do the same thing. Move the c to this way, move this way. We get negative 2 equals 0. The c's cancel each other out. I have to subtract the c, and I have to add the 1. Subtract the 1. And so I get this. Well, that doesn't make any sense because they don't equal. It doesn't tell you what c equals. And there's a problem here. The problem here is we can't solve this initial value problem. This initial value problem doesn't yield a solution. And it has to do with a lot of what we did in this problem, mainly from the very beginning. But the big thing is it didn't pop out what we wanted, which was this equation. And there's a reason for it. The reason for it is from the very start. dy dx equals y squared minus 4. What we did is we divided by the y squared minus 4. So we got dy over y squared minus 4 equals dx. The second we divided by this, we're assuming this doesn't equal 0. Well, when would it equal 0? It would equal 0 when y equals 2 or negative 2. And so we were still able to recover this solution from the ultimate from the solution to the differential equation. But we were never able to recover this one. And that's going to happen. Sometimes you're not going to be able to recover either of these. Because the second we do this, we're assuming this doesn't equal 0, and anytime it does equal 0 can no longer be a solution to this differential equation. Now, this isn't that big of a deal right now, but it is a consequence of the way we solved it. So what are we going to do about this? Well, nothing, right? There's nothing we can do about it. This is the equation we wanted to solve. The only way to solve it was the way we did it. And so we just have to, accept the fact that we're going to lose solutions along the way. Now, we're going to learn more ways of solving these differential equations. And if we can come up with a way of solving this differential equation that doesn't make us divide by the y squared minus 4, and so that we don't lose any solutions, Well, that would be a preferable way to what we just did. Even though it might not be easier to do, it might be preferred because we won't be losing any solutions. So just a rule of thumb as you move forward. If you could solve this in multiple ways, but one way would result in you losing possible solutions to the differential equation and another won't, well then choose the one that doesn't make you lose solutions. Okay, so this one is going to take us a little bit longer to get through. I mean, they range from very, very easy to a little bit more difficult, but I don't think these and any of these become all that difficult. It's all a matter of do you know how to do the integration that results, which would probably be the hardest part, and it's just a matter of getting back into that integration. You need to know your integrals. So anyway, we can't separate this one again. What do we got here? There's an initial value problem attached to this, so we'll ignore that for a second. This e to the y I'm going to bring over to the y side by dividing it. This cosine x, I'm going to divide over to here, and I'm going to multiply the dx over, so all that manipulation gives me e to the 2y minus y over e to the y dy equals sine 2x over cosine x dx. Now before I start integrating this thing, what I'm going to do is I'm going to simplify a little bit. So this I'm going to split apart into two separate fractions. This I'm going to use an identity. Sine 2x is a double angle, and that's 2 sine x cosine x. That's a double angle identity, which will allow me to cancel this cosine x down here. So ultimately I'm going to get, divide these two, it's going to give me just e to the y, minus these divided here would give me y e to the negative y, I'll just bring it up, that'll be dy, equals, if I do this substitution here with this identity, the cosines cancel, I really just get 2 sine x dx on that side. So now I'm ready to integrate. So I integrate this side, I integrate this side. Simple integral here, by parts integral here, simple integral here, and then we're good to go. So we've done this one enough times now. I'm going to say your u is going to be, I'm going to put the negative in here just to carry it along, so negative y, and the dv would be e to the negative y dy. Du would be negative dy, v would be negative e to the negative y, and so we're going to get, this is e to the y, plus, I'm doing plus because I already put the negative into this substitution. So this times this, which is a negative times negative, so positive y e to the negative y, minus the integral of this times this, so those two negatives would cancel, but I still have to subtract it with the by parts, and so I would have merely just the integral of e to the negative y, which we've already done, which is negative, so that switches back to a positive, e to the negative y, and then the other side is just the integral of 2 sine x, which would be negative 2 cosine x, throw a plus c somewhere, and there's our answer. Now that's just the answer to the differential equation. We then have to solve the initial value component, which is basically ultimately figuring out which c would satisfy this condition. Well, x and y are both 0 here. So if x and y are both 0 here, this would be e to the 0, which is 1, plus 0 e to the 0, which would be 0 times 1, plus e to the 0, which is 1, equals negative 2 cosine x, x being 0, cosine of 0 is 1, so it'd be negative 2 times 1, plus c. So what do we get here? This is 0, this is 2, this is negative 2, divide it, so c equals negative 1. So e to the y plus y e to the negative y plus e to the negative y equals negative 2 cosine x minus 1 solves the IVP. This one here solves the differential equation, and this solves the associated initial value problem.